row that are all connected. Okay, so when we're doing these units 4, 5, and 6, they all kind of build on each other. It just keeps going and progressing. Okay, I call this one relations and functions. Then we're going to move on to creating lines. That'll be unit 5, and then unit 6 will be having multiple lines. So it all just builds on itself. So it's almost going to feel like one massive unit, and it's going to be hard to kind of decipher which one we're in. I forgot what I was going to say. I just completely blanked. Might as well just get started. Today's going to be pretty easy. It's going to be a little bit of review. We'll do a little bit of work, and then we'll probably start the actual unit today as well. So we might do 2 lessons in one. This first page, we're not going to talk about at all. It's like the history on Cartesian planes and the Cartesian coordinate system. It's about an old dude who invented a way of putting graphs on things. So a Cartesian plane, it's the only thing you really need to know. This terminology right here. Cartesian plane. That's like an XY graph, right? You've seen these before. So a Cartesian plane is something that looks like this. We call Y's going up and down. We call X's going left and right. And it's a way of like putting plot points on a graph. That's what we call it basically. It's called a Cartesian plane. Right? You don't really need to know the history about it, but you're probably going to hear that terminology. And you're going to be like, what the heck's a Cartesian plane? It just means this, XY graph. Awesome. Let's do a little bit of review on how a Cartesian plane works. So what a Cartesian plane is doing is telling you like how far left to right, how far up and down you're moving. And it always starts from the very center right here. This is called the origin. Right? X tells you how far left or right to go. So if I said you want to go 2 to the right, that would mean X equals 2. That means you have 2 to the right from center. And if I gave you a Y value, I said Y is 5, that means you would go up 5 from the center. And any given point has an X and a Y value. All right, let's start with point A. Point A. So if I look on my graph, I'll be able to find point A. It's right here. If I wanted to figure out the location of point A, if I wanted to describe it, I need to describe how far to the right it's gone and how far up it's gone. And in that order. Okay, so you do left, right first, up, down second. So this thing went 1, 2 to the right, and then 1, 2, 3, 4 up. That means the location would be at 2, 4. And then we put a bracket around it. That is called an ordered pair. It always goes in the order of X, Y. How far left, right, how far up, down, from the origin. Okay, we can try another one. So we'll look on our graph for point B. I'm going to do that like I knew what I was doing. So we look for point B on here. We have point B right here. If I want to figure out the ordered pair, or where that is, the coordinates of where it is, you start at the center, you figure out how far to the left it's gone. It's a 1, 2, 3 to the left. When you're going to the left, we call it negative. So that would be negative 3 to the left. Comma, how far up and down it's gone. It hasn't moved up and down at all, right? It just went 3 to the left from the origin, and then it stayed there. It means it went 0 up, down. The ordered pair, negative 3, 0. That's the location of point B. Awesome. Do the next 3 on your own. So see if you can write C, D, and O. And I'll put my answer up on the board so you can follow along. Awesome. So I label all those points. I tried to color code them so they stick out to you. The blue one was point C. It's all the way out here. That thing was 6 to the right and then 3 down, so it'd be 6 comma negative 3. If I look for point D, which is down here, it never moved left or right. It just went straight down to negative 3, so it's at 0 comma negative 3. And the last one, O, is at 0 comma 0. This one does have a special name. It's called the origin. It means the very center of the graph, right? It's the origin, point of origin. Awesome. This stuff rings a bell, I hope. Good, good. The next thing that we just need to talk about is another way that we describe these Cartesian planes. So we obviously order pairs to describe where things are. We have another way of generalizing where things are. Right? And the way we do that is by making this graph into coordinates. So if you look, your graph is cut up into 4 chunks. Right? Like there's one chunk here, right? One here, one here, one here. We do have names for those areas. This one is quadrant 1. So you always start there and then go counterclockwise. So you're going to go backwards. That's how you name the coordinates. This one would be coordinate 2. This one would be coordinate 3. And this would be coordinate 4. So instead of having to give an exact ordered pair of where something is, I could generally describe it and just say it's in coordinate or it's in quadrant 1. Right? And that would mean any point that's up here in the top right corner. So for instance, the next question says, write the coordinates of the points in the second coordinate. So if you're looking, there's one point in the second coordinate. The only point in the second coordinate is E. The point for E is at negative 2. It went 2 to the left. And then 1, 2, 3 up. So negative 2, comma 3 is point E. It's the only one in the second coordinate. Awesome. You'll notice that point B is on the line. It's on the x-axis. That means the left-right line. That means it's not in quadrant 2. All right? It's just on the axis. It doesn't actually fall into one of the coordinates. It's on one of the boundaries, essentially. Awesome. Number C. You guys can try that one on your own. So write the coordinate of the point in quadrant 3. So if I were to look up here at my 4 quadrants, quadrant 3 is this area over here. Quadrant 3 has one point in it, point F. That point is located negative 4 to the left and then 3 down. So 4 left, 3 down, that gets you to point F. Awesome. A couple of things that we can generalize about the quadrants. We can describe them as being positive or negative for their x or their y-axis. So for instance, I know if I was in quadrant 1, I have a positive x because it went to the right and a positive y because it went up. Right? That kind of makes sense. If you just generally talk about the numbers, you might not know what they are, but you know that it's going to be positive and positive if I'm in quadrant 1. We're just going to fill out a little chart just to generally talk about it. So if I'm looking at quadrant 1, all the x coordinates would be positive, all the y coordinates would be positive. Because quadrant 1 is to the right and up. Quadrant 2 is to the left and up. So if it's to the left, that means it's negative. And if it's up, that means it's positive. quadrant 3 is down here. That means I went to the left and down. If I go to the left, that means I'm a negative x value. And if I went down, that means I'm a negative y value. And my last one, quadrant 4, went to the right, which means I'm positive, and down, which means I'm negative on my y value. Again, just generally talking and understanding where points are going to be and how they work, this helps out. We actually use this skill a lot in Math 20-1 when we get to our trig unit. Just kind of useful to generally talk about where things are rather than exact location. Fantastic. I hope that's like all review. And if not review, at least simple enough that it feels like it. Okay, we're going to talk about patterns. So you guys did some of this in grade 9 as well. We're going to talk about how you can list patterns as X, Y things. And then we're going to talk about something called discrete and something called continuous. We're going to start this question with toothpicks. Okay, basically a line is a toothpick. It said 3 toothpicks are used to form a triangle. 1, 2, 3. A second triangle is formed by adding 2 more triangles, 2 more toothpicks. So if you look, I have my original one right here, 1, 2, 3, and then they added 2 more toothpicks to create a second triangle. And I have one triangle there, one triangle there. Again, a third triangle is formed by adding another 2 more toothpicks. So I have this, I have the first 3, then I have the next one, and then I have my third triangle. So you'll notice I'm gaining a triangle every time I add 2 toothpicks to the end of it. And if I put 2 more toothpicks, I get a 4th triangle, 2 more toothpicks, a 5th triangle, and so on and so forth. Draw the next 2 diagrams in the pattern. So the next 2 diagrams in the pattern would look like this. That's the original. Then we have another one. We have another one. And we have another one. So I would have 4 toothpicks, or 4 triangles here with 1, 2, 3, 4, 5, 6, 7, 8, 9 toothpicks total. If I wanted to do the next drawing, I would do the exact same thing again, just add 2 more lines on the end, and I gain another triangle. So 1, 2, 3, 4, and 5. That would be the next picture. This is following a linear pattern, right? Meaning that every time I add 2 more toothpicks, I gain 1 more triangle, and that relationship never changes. It just continually grows like that. We can represent that with this beautiful little chart right here. The top line is the number of triangles. So you'll see we started with 1 triangle, then 2, then 3, then 4, then 5. The bottom line is talking about how many toothpicks it takes to create that. So to create 1 triangle, I needed 3 toothpicks. If I look back up at my picture, to get 2 triangles, I needed 5 toothpicks. The next picture, to get 3 triangles, I would need 7 toothpicks. Then 9 toothpicks, then 11 toothpicks. You'll notice this relationship is constantly the same all the way through. If I add 1 to my triangles, I have to add 2 toothpicks. Gain 1 triangle, gain 2 toothpicks. You guys would have done that kind of stuff last year. I don't remember exactly how they taught it last year. I think they would have done things like this. You would have seen this like +2. Right? And then they would have done +2. This one was +1. Does that look familiar? People did things like that. I think this kind of what the new grade 9 teacher was. But they were just looking and seeing that the pattern was consistent as you went up your chart. Awesome. We like to represent this information as ordered pairs on a Cartesian plane. Right, where you make one of these things X and one of these things Y. So if you look, they've drawn a little thing for you already. Drawn a little Cartesian plane. You'll notice that they've labeled the Cartesian plane for you. So when it goes left to right, that was T for number of triangles. The up down was P for the number of toothpicks. So if you look at our chart, that means triangles is our x, left to right, and picks is our y, up, down. And now I could take these points and put them on the grid. The very first point would be at 1, 3. 1 to the right, 3 up. I'm like just too big. I just can't quite get on there. So my first point would be at 1 triangle, so 1 to the right, 3 up. 1, 2, 3, right there. That point represents that it takes 1 triangle for every 3 toothpicks. Then I do it again. The next point is 2, 5. So for 2 triangles, 2 to the right, I need 5 picks. 1, 2, 3, 4, 5, right there. Then I can do it again. For 3 triangles, 1, 2, 3, it was 7 picks. And then again, and then again. And you'll notice that this linear pattern, where it's going up by the same, when you put it on a Cartesian plane, you can visually see it's a linear pattern. Right? It's going in the exact same path. People see that? Yeah, it's just following that path. Awesome. Today we're going to discuss connecting the dots or not connecting the dots. So on a graph like this, these points represent how many toothpicks it takes to create a triangle. Currently, we don't have the lines connected. All right. Would it make sense to connect the lines? And what does it mean when we do connect the lines on a graph? All right. So if we try, let's just connect the line and then see what it means. So if I do this, I'm going to connect these dots. So the straight lines I'm going to draw on this board. You probably don't want to draw that on your thing yet, but we're just going to talk about it. The dots before told me how many toothpicks it took to make a triangle. By connecting the lines, like this, connecting the dots, what I'm saying is that it's possible to have a point right here. This means that it would be 1.5 triangles if I had 1, 2, 3, 4, and a little bit toothpicks. In this example, would it make sense for me to have 1.5 triangles and 4.1 toothpicks? Is that possible? Is that realistic? That someone's going to have just chunks of a triangle and just chunks of a toothpick built out? Probably not, right? Like, we were always adding exactly 2 toothpicks. We were never adding half toothpicks or quarter toothpicks or anything in between these 2 points. By connecting the dots, you're saying that all of these points in between exist, that all these situations are possible. And in this question, it's not possible. You're not going to have partial things. You're only going to have these points. The terminology we call this is discrete data. All right. I've explained that kind of in words and a long story. We'll put something up there together. So explain why it does not make sense to join the points in a straight line. I'm going to put because, which you shouldn't start a sentence with the word because this data I'm going to say makes jumps. It's not a perfect mathematical terminology, but it makes sense when we talk about it. The data jumps. I jump from 1 triangle to 2 triangles. I don't have 1.1 triangles or 1.3 triangles. I jump to the next thing. Right? I don't gradually grow. Right? So I'll probably use that terminology just because it's an easy term for us to use. I'll say jumps, or there's gaps in the data. Describe in words the relationship between the number of toothpicks and the number of triangles. In words, the way I would describe this is the number of triangles goes up by 1 for every 2 picks. So anytime I add 2 picks, I gain 1 triangle. Awesome. This says write an equation that can be used to determine the number of toothpicks if we know the number of triangles. That's something that was harder from last year. One of the harder things you guys would have done. What you want to do is you want to look at your data up here. I think it's easier to look at the chart for now. In the future, we'll look at the graph. So you look at this. You're going to write this out using T and P in some sort of like mathematical equation. The trick is to figure out how much you're jumping up by. So that's why you guys would have done these like little jumps right here. And you would have +2, +2, +2. Hopefully that makes sense and you guys remember that. On the top, you would have also done some sort of jumps like +1, +1, +1. The question said that they wanted to build an equation to represent the number of toothpicks if we know the number of triangles. So toothpicks would be the first letter. The number of toothpicks is equal to whatever you're jumping up by. Okay, so we were jumping up by 2's. So it'd be 2 times the triangle. So I took my number of triangles and I multiplied it by 2. That means if I had 1 triangle and I multiplied it by 2, I'd be at 2. If I had 2 triangles multiplied by 2, I'd be at 4. If I had 3 triangles multiplied by 2, that'd be 5. But that doesn't quite work out. We're always 1 short because you had to have 3 to start things off. So you do something like that. 2t plus 1. We're going to get more into building equations. That's kind of a review from last year. Maybe you remember it, maybe you don't. I wouldn't stress too much about it right now. But what this means is that if I want to figure out how many toothpicks I have, I take the number of triangles, multiply it by 2, and then add 1. And that would always tell me how many toothpicks I had. We'll use that equation for G and H, which is actually a skill that's a lot more important. So use the equation to determine the number of toothpicks if there is 27 triangles. 27 triangles. That means T equals 27. I'm going to put that into the equation. So P equals 2 times 27 plus 1. If you put this in your calculator, it will tell you how many toothpicks you needed to build 27 triangles. You put this in your calculator the exact way you see it, 2 times 27 plus 1. If you do that, you'll figure out that the number of toothpicks it would take would be 55. Again, this is some pretty fast review. We will get more into this stuff. You could also use the equation to go the other way. Okay, that means you could have a number of toothpicks and figure out how many triangles you have. All right, to do that, so look at question H. It says you have 83 toothpicks. How many triangles do you have? That means they told you that P equals 83. So you're going to go back to your original equation, and you're going to change P to be 83. I'm going to give myself some space to work here. 83 equals 2t plus 1. To this equation, I changed P to be 83. Now, the first time we did this and we changed T, it was easy because P was already by itself over here. And we could just put this in our calculator to figure out what P was. This question's harder because T is not by itself. T has all these numbers surrounded around it. And we're trying to figure out what T would give us 83. Now, you could guess and check. That's a very poor way to do it, but I guess you could. The better way to handle this is to isolate T. Hopefully that's the terminology you've heard before. Maybe they just said get T by itself. Right? So what we're going to do is we're going to mathematically isolate T, get it by itself. To do that, we're going to move the numbers away from T so that they're on the other side of the equal sign. You guys remember bedmass? So bedmass was like your order of operations on how you do things, right? Like we always say that you do anything inside the brackets first, then you do your exponents, then you do any division, multiplication, and that's how you calculate numbers. Reverse bedmass is how we get something by itself. So when we're trying to get T by itself, we want to undo any additions or subtractions that are next to the T. If you look at this, I have a plus 1. The opposite of plus 1 is minus 1. So what I want to do is subtract 1 from both sides. When you subtract 1 from both sides, it'll cancel out on the right side, and then you'll have a new calculation on the left side. 83 minus 1 equals 82. Equals 2t is still there. The 1 was canceled out by the minus 1. So I moved a number, I showed how I moved it, and then I reorganized my work. I rewrote it out. And I just keep following that process until I get the letter by itself. So I have another number here. It's a multiplication, which is the next thing I need to move. To move something, you want to do the opposite of it. So the opposite of multiplying, which is 2 times t, would be division, right? Opposite multiplication, division. We're going to divide both sides by 2. When you divide both sides by 2, it'll cancel those 2's out so that you only have t left over. On the left-hand side, you go 82 divided by 2 in your calculator, and you'll get 41 equals t. That means you have 41 triangles if you had 83 toothpicks. This skill and this stuff like G and H, we're going to do a lot of. And it's also going to be very important stuff, like very useful going forward. Fantastic. I think we have one example left. And then we'll be done, I think. So, yeah, pretty much. This one is the exact same idea, it's just a different situation. So this is students in a physics classroom determine the resistance of an electrical circuit by measuring the voltage when amps were passed through the circuit. The table shows the result below. So if you look down, you'll notice that they've got their table right here. This is the amps, this is the volts. We're going to put this data on our grid. You look at the grid, they've already drawn it for you. They didn't label them, so they didn't make one V or make one I. So we get to choose which one's X and which one's Y. They made the grid about the same size. One side is bigger than the other. Not really, hey? What we're going to do is we're going to make this X and this Y. And when we look at our grid, we're not going to count the X's as every single brick. Right? So So if you look, instead of saying every single block is 1, I'm going to say every 5 blocks is 1. So 1, 2, 3, 4, 5. Like that. My reason being is I want to try to use as much of the grid as possible. Okay, and if I did the first 4, my grid would only go about this far out, right? And it would look kind of silly. I want to try to use the entire page if possible. And by looking at my chart or my data, I know that my x's don't really go above 4. Like look at my amps, right? It goes from 0.5 to 4. It's not very far. So that's why I spread out my data to every 5th block. For my volts, though, I go from 0 or 6 all the way up to 48. So I am going to do every individual block counts as 1. All right, so if I'm looking at my y's, that means it would be 1, 2, 3, 4, 5, 1, 2, 3, 4, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Actually, this may not be good enough. No, it's not. So we're going to do every 2. Every 2, 4, 6, 8, 10. 2, 4, 6, 8, 20. 2, 4, 6, 8, 30. 2, 4, 6, 8, 40. And the top one would be 50. Right? So just be aware that the scales don't have to go by 1. Like every line doesn't have to count as one thing. Always check your scale when you're looking at a question on a test. Fantastic. All right, we're going to try to plot these things. All right, so the first point is at 0.5, 6. So if you're looking, 0.5 would be halfway between 0 and 1, so okay here, and then up to 6, 2, 4, 6 right there. That would be my first point. I'm going to do it in blue. See if you can do the next 4 points. Okay, so keep going on that trend. So the next 4 points would be 1.5, 18, 3, 36, and so on and so forth. Awesome. So if you look up, you should have 5 points pretty similar to mine. Okay, those represent the different spots where you have different amps with different volts. Awesome. The second question says, does it make sense to join the points together in a straight line? So remember, to join a point in a straight line means that you're saying every single point along that line is a situation that's actually possible. On the last question, it wasn't possible to have half of a toothpick. Right? We were always just adding a full toothpick or not adding a full toothpick. You either gained an entire triangle or you didn't gain a triangle. Right? You never had 0.3 of a triangle. It never happened. In this question, we're all not physicists in here. I definitely am not. But when it comes to electricity, is it possible that I could have, 2.1 amps going through something? And is it possible to have 30.5 volts? Is it possible to get decimals in between there? Is it possible that these things just gradually grow, or does the circuit just all of a sudden get an extra 5 amps and it just instantly jumps to the next point? The answer would be that it is possible to have decimals. It is possible to gradually grow in between. It doesn't have to go jump and then jump and then jump the same way that the triangles did. So this is a question where we could connect the dots. And watch this. Actually wasn't that bad. Thank you. If you do this, I would recommend that you use a ruler of some sort or some sort of flat edge to draw straight lines. On your calculators, if you have older calculators, the back pops off and like the battery casing, and it's like the perfect thing for a little ruler on a piece of paper. Anybody else, try to use the lid of the ruler or something, just a straight edge so your pictures are decently straight and not all wiggly. Awesome. The reason that this stuff makes sense is because you can have decimals. Right? It makes sense that you could gradually grow up your voltage on something. You don't have to just jump from one thing to another. Awesome. We can use this graph to answer questions for us. So for instance, question C says, use the graph to determine the voltage for a current of 2.5 amps. What we're going to do, we're going to try to figure out where on this line that you have 2.5 amps. 2.5 amps means that you have gone over here. You've gone 2.5 to the right. Where on this line do you have a point that is 2.5 to the right? So if you look along this line, this is all 2.5 to the right. Eventually, you'll find a point. This point right here has 2.5 to the right. Actually, that's not 2.5, that's 2.4. Can I move lines? Is that possible? It's not. I apologize. 2.5 is halfway in between. I was not halfway in between. 2.5 is right here. If you go up from 2.5, you'll figure out a point on your graph that has gone 2.5 to the right. You can then look at that point and try to figure out what the voltage would be if you've gone 2.5 to the right. My voltage would be about here. Let's call that 29. 28 would have been this point. 30 would have been that point. I'm about halfway in between. So I'm going to say 29 volts. So once you have a beautiful little graph like this, you can actually use it and try to read it for different points. Fantastic. We have write an equation expressing V in terms of L. So if you're looking at this, it's a little bit harder to tell the trend. The reason it's a little bit harder to tell the trend is because they use decimals in here and all kinds of stuff like that. The trend is that for every 1 amp, so from here, 1 amp, you're going up 12. And that's the trend that they have. Again, that's a last year skill. Hopefully you kind of remember it. If not, that's not a big deal. We will get going more and more on our building equations. Like, we're going to build up to that stage again, so don't worry too much. Our equation could be written like this. The number of volts equals 12 times the number of amps, which was the letter I. Question E, use the equation to determine the volts when the amps, or when the current is 6.2 amps. They told you that I equals 6.2. So you need to go back to your equation and change I to be 6.2. Like that. So we went back to the equation, we changed the letter they told us, and then we try to get the other letter by itself. It's already by itself, right? V is by itself. So I just need to put this in my calculator.
If you put that in your calculator, I don't know what the answer is.
Anybody try it? 70 something, I'm guessing.
74.4.
74.4? 74.4. That means if you had 6.2 amps, you have 74.4 volts. Fantastic. We're not going to do question F because I don't think we need to be talking about resistance or rearranging circuits or any of that jazz. Okay, we've done, yeah, go ahead. Definitely. We've done two questions. We've done one without jumps and one with jumps. The way we describe those two things, or the terminology for those two examples, is discrete versus continuous. Right? Discrete data. Discrete info has jumps. Continuous data doesn't. It gradually grows. Everything's connected. And I'm just going to put connected for you. So if you think about the two questions we did, we did the toothpick question, where you were adding two toothpicks and you were jumping to one new triangle, and it was always leaping like that. That's called discrete information. Continuous information is like the volts and the amps. Everything was connected, right? We grew gradually. You didn't just all of a sudden have 100 amps, right? It gradually could grow to that point. We're going to do a bunch of different examples of discrete versus continuous. You will get tested on stuff like this, of do you know what discrete and continuous is? So for instance, classify each of the following variables as discrete or continuous. We'll start with the time taken to complete a 100-meter sprint. So, if you ever watched the Olympics, they time it down to like, I don't know, the thousandth now, right? It's like pretty accurate. When you talk about people finishing a 100-meter sprint, does it go from, you finish it in 10 seconds, or you finish it in 11 seconds? Or is it possible that you could finish it in 9.3 seconds? Is it possible that you gradually were growing that time from the lowest possible time to the highest possible time, and you could finish anywhere in between? Or does it make more sense that you jumped? You're either this one, or this one, or this one. Either 9 seconds, or 10 seconds, or 11 seconds. This would be an example of continuous data, because it doesn't jump. It's gradually growing. Almost always, with time, time's usually a giveaway that it's going to be continuous, because time is gradual, right? When I start the watch, it's gradually going from 0 seconds until I finish. It doesn't just jump. Right? It doesn't go from 1 second to 2 seconds to 3 seconds. It gradually got there. There's all those decimals in between, and you could finish at any one of those decimals. Unlike question B, which is the number of students who will pass Math 10. So if you look around in the room, we got 27 of us. 1, 2, 3, 4, 5, 6, 7, 8. 30, 40, 50, 60, 70, 80, 90, 21, 22, 23, 24, 25, 26, and 2 in the bathroom, 27, 28. So we've got 28 people. If we wanted to count the number of people who will pass this class, is it possible that I'm going to have 24.3 people pass? Or am I going to go from 24 people pass to 25 people passed? Is it just going to jump for every person who passes to the next spot? Yeah, it's going to jump, right? We start with 0. None of you have passed yet. Right? And then by the end of the year, we just slowly keep adding. So it's like, hey, now 1 person has passed. Now 2 people have passed. Now 3 people have passed. At no point am I at like 4.3 people passed. Or 22.7 people passed. Right? It jumps from one to the next. You either passed or you failed. This is an example of discrete data. It jumps. There's no in between. Question C, the height of students. So let's just pretend like you growing. Okay. Do you go instantly from being 5'6" to 5'8", or did you gradually grow and get there? At some point, were you 5'6" in a little bit, right? And then 5'7", and then 5'7" in a little bit, and then a little bit more, and then a little bit more. You don't just wake up one day and you're 6 feet tall, right? It'd be pretty sweet, but it doesn't work that way. This is continuous.
So does your unit of does your unit matter when you're doing this? Because like if you're measuring everything in inches and then a person is like a millimeter taller, is that like?
Yeah, that's fair. No, it doesn't. It doesn't matter. I keep spelling continuous wrong. No, so they're changing between like inches and centimeters and stuff like that. No, that wouldn't matter. It's just the concept between your height and how you're growing. Awesome. The last one, which is an example that we've used a lot before, is shoe size, which throws people off because people are like, well, your foot grows and doesn't just all of a sudden grow, right? Like it slowly, gradually grows. But this isn't talking about the size of your foot, it's talking about your shoe size. So for instance, if I look at my shoe size, I went from a size 9 to a size 9.5 to a size 10. I'm jumping in half increments, right? I can't go to the store and buy a shoe size of 9.2. Right? This is shoe size, like the size that it's coming in. I understand my foot gradually grew, but my actual shoe size was jumping. Right? It's like your shirt size. Right? Like I grew as a person, but my shirt size jumped. Right? It went from a small to a medium to a large. Right? It's jumping. So shoe size is actually discrete. And the reason it's discrete is because my actual shoe size jumps from every single level to the next level. I can't buy a 9.1 shoe size. Even though that's probably what everybody here needs, right? It's some specific measurement. You gotta be like a pro athlete to get that kind of treatment. That makes sense? Jumps versus doesn't jump? Continuous versus discrete? Fantastic. I'll give you guys the rest of class, which is good, like 20 minutes.